Well, welcome. We're going to do a little bit different video for this week's lesson, primarily because we utilize a lot of technology, and show those and describe what we're doing, thought it would be easier just to highlight them on the screen as we go through this week's examples. All right, in this example, we want to consider the set of linearly independent vectors in R4. So we have these three, and we want to extend this to a set that spans all of R4. So to do this process is not the only one, but it will get us there. The first thing we want to do is identify what we call T1. Okay, this is a set that we already have. So our three given vectors, which you see here, is T1, as V1, V2, and V3. Okay. Once we do that, then we're going to augment that with the identity matrix. This isn't the only matrix that'll work, but it's the easiest and most direct one. So we create an append these two matrices together. So we have T1 and T being the identity matrix. Once we do that, then we're able to construct a new matrix and use Gauss-Jordan elimination to find the resulting vectors that we need. Okay. This will indicate we only need one more vector, and so in the reduced row echelon form, this will highlight the vector. It'll be like a signpost of the vector that we need in order to append it to our matrix in order to have a complete basis for the subset of R4. Okay, so in doing row reduced echelon form of the matrix, you can see here what you've highlighted in yellow indicates that the third row is the one that we want, and that's from our original matrix E that we appended to it. So the actual fourth vector that we're looking for is the one that you see the arrow pointing to, okay, which is the third row of the identity matrix. Okay, so if we put that in, then we have our new basis, which is T2, where we have appended the T1 matrix, what I call T1. I guess I should have called it maybe T3 because it's the third column of the identity matrix, to our set S, and that creates then a basis for all of R4. Okay, now we're going to do one more example with a very similar result, but just kind of fast forwarding through the process. So identify the matrix. As you can see there, our S is our identified one. We're going to use the identity, which I plugged into GeoGebra and did row reduction on. The reduced row echelon form indicated that the first vector was the one that we would need, and so I've highlighted that there like I did in the previous one with the yellow oval, and that means then that the final vector for our basis is going to be the first vector of the identity matrix for this example. And so our basis set is outlined there, where we have the first three V1 through V3 vectors, and then our this is actually literally the T1 vector, if you consider the subscript to be representing the number of the row of the identity. So that is the new basis for this set for R4, given these three linearly independent vectors. Okay. All right, moving on. Our next example was finding the null space. And so to find the null space of this problem, you can see we have that linear system of equations, which I inputted in to GeoGebra, which you can see on the right there. Using the row reduced form, I get this set of equations. So you can see that I have three pivots along the diagonal there, and then I have my x4 and x5 are a linear combination of the first three vectors. So solving this system, remember the null space is the set of vectors that makes the system AX equal to 0, or solves the homogeneous equation. Okay. From our previous theorem, we know that we have 3, and so we subtract from our 5. That gives us the 2 free variables, which we were expecting, and we can see that here. So solving this, in case you're wondering about the signs, in the row reduced echelon form, remember those are x1, x2, x3, x4, x5 equals 0. So to solve for x1, x2, x3, I needed to move those columns over. So I mean, it's doing the inverse operations, which is why the signs shifted. And that utilizes the 2 free variables s and t, which then those two, if we look at the linear combinations of those bases, of those 2 vectors, that creates the basis set then for what you see in the curly brackets there for our null space. That creates the basis set for a null space. Okay, I hope that was helpful. All right, next, we want to look at the rank of the matrix A, and specifically determine the column rank of A. So our matrix A here, I input this into GeoGebra, and we can also find the column space at the same time. So I'm going to do both of these things together in the next slide. Okay, so here you can see that I inputted the matrix in, and looking at the row reduced echelon form, that produced the column space of A. It's generated by all 7 of those vectors. And the basis for that set, as you can see from the row reduced echelon form, would be found from V1, V2, V4, V5, and V6. So V3 is a linear combination of the other vectors in that set. And so that gives us the basis for the column space, and the rank then can be defined as such. The column rank and the all of those values have the column rank, the row rank, and the rank of A all have the same value of 5. Since each of the rows in the row space is identically equal to the 5 vectors, and the dimension of it is actually, or the basis set, if you will, of that is actually each of the rows of A. So the rows are not a linear combination of each one. Each one is distinct. The columns, however, are a linear combination. And so you get the resulting values that you see there. All right. Well, I hope that was helpful, and I'll see you in the next video.